Okay, great. Thank you. Thank you for the introduction. I'm very happy to be here. So actually, this is my second time to be Singapore. So last time I was there like only for 1 day. The weather is the same. People are like very nice. So, this morning we already hear a lot talk about enrichment design for selecting treatments, comparing treatments, but they always focus on single stage treatments. So the talk I'm going to talk about today is for us for this dynamic treatment regimen. So if you're not familiar with the dynamic treatment regimen, I'm going to give you a brief introduction during my talk. And if you have any questions, need to clarify, please feel free to stop me. And by the way, this is a joint work with Yuan Jia. She's in the audience, and her former student, she's at Wisconsin right now. So, all right. Well, first I'm going to give you like a brief introduction why we want to talk about this smarter. Well, it's not smarter, it's like smart plus enrichment kind of design. Especially we think it's kind of useful for DTR. So by the way, this is more like a conceptual framework. I don't want to say like in practice, people have been using this design right now. Is this kind of idea we think might be very useful to discover treatment regimen, especially dynamic treatment regimen for personalized medicine. So first is like a personal medicine. So as you can see, I always quote this picture, even though he's no longer president right now. So, but in the personal medicine, in this PCAS, personal medicine refers to tailoring a medical treatment to individual characteristics for each patient. So in other words, you really want to treat the patient's individual base. So that's kind of very hard area in practice and also in statistics. So obviously related to the specific question is, I think at this point, talk about which drug, what kind of order of drugs, supposed to have different sequence of drug, which one you want to apply first, then second, and when or for whom you're going to use a drug or what kind of dosage you want to apply to each patient. So everything this is related to personalize. So I know people try to use precision medicine or type of thing, but I agree precision medicine, I feel it's more like a biomolecular kind of personal medicine you mentioned in the talk. So we're here talking about general context of personalized medicine. So in the personal medicine, one important concept is called the DTR, or stands for like dynamic treatment regimens. What's DTR? DTR is like a sequential decision rules. So because think about like when one patient comes in, you give one treatment at this point, and you follow patients, and you observe more things, right? You can see the drug beneficial, or maybe it has a side effects, or something come up. Then maybe next time you want to use different treatment, or you want to increase dose or decrease dose. All this is like a dynamic, is a dynamic decision. So this kind of decision rule basically try to tailor in at each stage for each patient's time-varying features and also intermediate outcomes. So because you observe something happening after first treatment, now you want to say, okay, next time, what kind of decision, what kind of treatment I should apply to this patient? So this is like a DTR. So why are people interested in DTR in personalized medicine? Well, first, we know this reflects clinical practice. Actually, this is not new concept. In medical field, people have been using this kind of concept or practice for many years. That's how they treat the patients. Whenever you see the doctor, they ask you all these kind of questions, and then they say, oh, I want to give this prescription instead of the other one. And also, we know that patients respond differently. So that tells you have to give a different treatment to different patients. And that we know drug effects that change over time. Sometimes works right now or may not work in the future. And sometimes a drug doesn't seem to work, but probably in the long term, it will be beneficial. So this kind of drug effect changes over time, so you need to account for the fact you want to adapt it to the patients to be able to see the benefit of treatment. And of course, there are a lot of things like going on with individual patients, like comorbidity conditions, and also there are relapse, there are side effects, adverse events, all this kind of thing going to happen in the treatment history. This kind of thing you need to think about when you want to give the best treatment for one individual. And also, like we know, if you do intensive intervention or treatment, it's very high cost. You really want to treat the patients adaptively, like going to reduce cost, and also increase the compliance of a patient. Because people think about you treat the patients based on his or her features. So, and DTR are very often used in cancer, psychiatry, substance abuse research. So I give you one simple example, try to describe what kind of DTR people might be interested in, but this is a very simple DTR. There are more complex one. So this is from like a ADHD trial. So actually from that study, basically I treated kids with attention deficit hyperactive disorder. So it's ADHD. So you can, there are two examples I demonstrate what's DTR. So first DTR1 is, okay, you start with medication as initial treatment. Now you follow this kid and see how they respond to this drug. So if kids respond very well, you probably say, oh, let's just continue this medication. However, if this kid doesn't respond, they may think about maybe this drug doesn't work perfectly. We need to augment with something else. And in this case, it's augmented with behavior modification. So you can see this is the case. We give a treatment to this individual patient, but depends on if this kid respond or not respond during between the first stage and the second stage, right? And the other one is like a kind of opposite. So start from behavior modification. If this works, continue. If it doesn't, we augment with medication. So this shows like a diagram how this pathway goes through from stage 1 to stage 2. So this is the dynamic treatment regimen. So what I'm saying, dynamic treatment regimen, so you can see very different from usual treatment strategy is a lot of cases like when you think about clinical trial, treatment is defined, well-defined at the beginning. But in this case, for individual, the treatment is not well-defined because we don't know if this patient is going to respond in the middle. And depending on if they respond or not respond, you can change the prescription in the second stage. So DTR, so it's not like a very well-defined some treatment strategy. Actually, it's a function, it's a policy. So the policy basically stay like this way. And how you're going to apply to this individual patient, you really need to follow this patient to see what's going on. But the policy is under this decision. So this is DTR. Okay, next one. So well, when you have, so you can think about you have so many DTRs going on. So the example I gave you earlier is a very simple one. But you can imagine the second stage of treatment can adapt to a lot of things, depends on what's going on in the middle, right? So there's so many DTRs. Well, how we come a good study, I mean like a reasonable trial, so that we can find out the best DTR for each patient. Or even don't want to get the best, maybe you have two different DTR, like for example, the previous example, suppose you have this DTR1, DTR2, basically like two policies. How are we going to design a study so that we can compare those two, right? So one simple example, well, we can just recruit two group of people and try to apply DTR1, DTR2, but actually this cannot be the case because even for the first group of patients assigned to DTR1, you don't know what's going on in the middle, right? And those patients, if they don't continue, they will be different. So in this case, what kind of design people use to try to make a valid inference for DTRs? And obviously, most of you probably know that it's called smart design. So let's call it sequential multiple assignment randomized trial. So what's smart? Smart actually, the idea is pretty simple. You have two stages. Remember previous example, you have the first stage and second stage. So in the first stage, basically you do randomization. That's what you do. So in this case, you can imagine in the first stage, I can randomize those kids into two arms. One is in medication, the other is behavior modification. So that's two-arm randomization in the first stage. And then in the second stage, for the same group of kids, you re-randomize them. And how you re-randomize, you can re-randomize, like say, here, for this group of patient case, because they receive medication at the beginning, you can re-randomize between two. One is continue, or the other one is add behavior modification. So that's a randomization in the second stage. And also same thing you can do that for the other arm, DTR2. So you can do a re-randomization. So essentially sequential randomization, just a very simple idea. Every stage you do randomization. But one thing I want to emphasize here, randomization, because of randomization probability. Those probability can be more flexible. For example, in the first stage, you can just pure randomization. But when you go to second stage, randomization probability can depends on how they respond or not respond after first stage. In other words, the second stage randomization can depend on what's going on in the middle, what's the intermediate response. So let it randomize. So that probability can depend on that one. For example, if they respond, your randomization probability to continue to be high, right? Like 80% or 20% go to the other one, which is added modification, for example. But what I'm saying, like a probability can be different depending on intermediate outcome, but still randomization. So in other words, every patient has a chance to be going to either arm in the second stage. All right, so this is smart idea. So I have two slides at the end of the talk, but probably I don't need to show. Basically, just demonstrate you why smart design can give you varied inference for any DTR. So in other words, so basically based on causal inference, this framework. But the key thing here is to randomization, because randomization can prevent you to have this kind of selection bias and prevent all this unobserved confounder issue. So there are a lot of studies implement this smart design. So I listed a few here. So you can see like ADHD I mentioned earlier, and also there's for depression study and the KD study, and also there's some study for prostate cancer study. So, but all of them are like a two-stage randomization trial. So, okay, so. Okay, right, so this, the next two slides, I just show you one particular study, which we quoted from this paper. So it's based show you how these two sequential randomization are doing and what's going on in the practice. So this study is, they want to study the effect of communication intervention for kids with autism, okay? So they want to test the effects between those two interventions. One is like use a speech generating device. The other one is brain development behavior intervention. So they want to say, in addition to this one, if we add this device, can we get something more? Can we improve their communication ability for this kind of kids, okay? So the second stage, I have a 12-week follow-up, and this, maybe I show you next, hopefully you can see that. So the first time they recruit, like it's 134 kids, and only 61 really go to this two-stage study. And at the beginning, they randomized 30 to this Jasper plus EMT, which is Jasper plus EMT basically is like a behavior developmental intervention. And the other group just go to Jasper plus EMT and add this device, okay? So this is the first stage. Okay, so so then we can see in this diagram, you can see during this first stage, there are like a few people drop out from this first stage. There are 3 here, 3 here. So the remaining one, they go to second stage, okay? When they go to second stage, there are 3 possibilities. One is if they have early response. In other words, the previous treatment worked well for this kid. So basically doing this continue. So there are 16 kids you can see continue with this treatment intervention arm. And if they have slow response, then so basically, in that case, they just increase the intensity. And there's a slow responder. Also, there's another 6 kids. They go to this same treatment but plus a device. So you can see in the second stage, there are 3 arms going on here. And for this group, in the second stage, there are 2 arms. One is add continue. The other one is increase the intensity. Okay, and after another like week 4 and 36 weeks, and you can see there are a few more people drop out from study. Okay, so this just diagram shows a very simple smart design people are doing for this 2-stage clinical trial. So, all right, so why smart is useful? So if you even from this diagram, you can see smart can do a lot of things. For example, because first stage randomization here, you can simply compare those 2 treatment arms. You can see if just plus EMT is better or compared to other device or not, right? You can compare these 2 main effects. You can also compare the two treatment strategy. Like for example, you can compare like this arm, just plus EMT at the first stage, then continue in the second stage. And then you can compare with, say, I start with the device, and in the second stage, I increase the intensity. So in other words, you can compare this arm, or this arm, or this arm. You can make all this comparison because they're randomization. Randomization protects you from all this kind of selection bias going on. So, but the most important thing, like for personal medicine point of view, is you can explore optimal treatment strategy. What's optimal strategy? Optimal strategy you cannot see from this diagram because this diagram is still like a fixed treatment strategy. Optimal treatment strategy basically is like a deep terrain. So in other words, you can decide what kind of treatment in the second stage for this kid, depending on all kinds of things or all kind of information you collect by this stage. Not just responder or not responder, maybe something else also. But all this kind of thing can be you can get information from smart design. Of course, assuming you have a large sample size. But if you don't have large sample size, you don't have rich information to infer individual treatment strategy. So let's kind of go to kind of motivating our design. You need a larger sample size. Okay, so this is just continue summarize what's the advantage of SMART. You can do very comparison different treatment options. You can discover adaptive treatment strategies, and you can even find a personalized treatment strategy as well. Okay, now comes to the limitation of this SMART. That's how we want to use enrichment, I call smarter. And we know like you try the operating cost of administrating a multi-stage randomized trial is not easy. Even for one single randomized trial, operation is not easy. And now you want to sequential randomize the randomization and get the patient consent from beginning and keep track of all the patient and get all the information you want. It's not easy. And usually as you can see, this length of a trial period is long because you have multiple stages going on. And one thing you already saw in the previous example, even though it's a very small trial, but you can also see some dropout, non-compliance issue come into the trial. Like when you go first stage to second stage, usually people drop out from study. Like for example, in Katie's study, originally grew about 1,400 patients in the first stage. Only one half of patients stay for entire 18 months of study. In other words, only half of them will go to next stage. And for other study, smart, like dropout rate was 70% in the first stage and the additional 13% dropout in the second stage. So in that case, we know like we want, for personal medicine, we really need a very big trial. We need a lot of patients so we can gather rich information. But unfortunately, try to do this kind of smart design, you always have people, you lose people from study. And once you lose people, you will get less power. So then it will be difficult to answer your scientific questions in personal medicine. So what we try to think about, can we use enrichment idea? So we have been talking about enrichment all the time, and but now this enrichment is not like this morning's talk of trying to enrich one particular subgroup. In this case, it's more like an enrichment stage-wise trial, as I'm going to show you soon. Okay, so the enrichment design we propose here is like a stage-wise enrichment design. So in other words, what we're doing is at each stage, we try to enrich the study population. So in other words, we recruit more patients, go into each stage. So idea is very simple. At each stage, you add enrichment sample, you recruit patients, and you recruit them into this stage and randomize them into treatments in this stage. And by then, so in other words, maybe next I can show you here. So you can imagine, forget about the right side first. This is like you standard SMART. Well, in the first stage, you recruit the patients and they randomize, and they go to the second stage, re-randomize them. So, but obviously, to be more practically, we just assume like some people can stay in the trial, go into the second stage, but some people can drop out from the trial, from the first stage, so they don't continue into stage 2. So enrichment, what we're doing here is, while in the second stage, this is example second two-stage trial. In the second stage, we recruit M subjects or M patients. Those patients in the first stage treatment can purely observational. So basically, just go there and grab a patient if they agree to go into a trial. And then once they recruit into stage 2, randomize them. And then now once you do, then at the end of stage 2, you have people here and also have this enrichment sample. And combine them, you can get whatever outcome you observe at the stage 2. So this kind of enrichment we are thinking about. So one key thing I want to mention here is for this enrichment sample, they were not in the SMART originally. So in other words, their treatment, their medication in the stage 1 is totally observational. So it's not randomized. It's whatever natural way they get from doctor, from clinicians. So this is a key of this design. So one extreme case, well, probably this is too extreme. So one extreme case is this. Maybe I go back here. Think about like suppose in the original SMART, or don't say original SMART, it's like people in the first stage, nobody go into second stage. Does that make sense? Nobody go into second stage. So in other words, you are really just doing one trial in stage 1. Now what I'm doing in this design, basically I'm doing is in the second stage, I recruit a patient to another trial. So this is also a special case of the SMART. So in that case, essentially this extreme case is we call like a meta combination of two different trials. One trial is done in the stage 1. Second trial is done in stage 2. And basically, we just combine those, then pretend it's like smart. But I know definitely it's not smart because they're different people, right? So it's just a different trial. And this can work too, or certainly under assumptions. So what I'm saying, like in a smart design, include this extreme case. So basically, two independent trials, now you put them together and make it like smart, okay? All right, so rationale behind why this is going to work. Everything is because it's randomization, okay? Everything is randomization. Firstly, if you are familiar with this smart or Q-learning idea or machine learning related, we know people usually think about backwards way, so start from stage 2 and now go back to stage 1, all type of thing. So now let's think about stage 2 first. In the stage 2, because in the stage 2, look at this diagram. In the stage 2, the people stay here, people stay there, they're randomized, right? And because randomization, this like the outcome observed really kind of like can infer this causal outcome. So basically, there's no bias going on. If you really want to compare the treatment at the stage 2, because they're randomized, they're no like observational. Now, the problem is what's going on with stage 1? Well, obviously, when you go to stage 1, you still want to compare treatment into stage 1. You cannot use those group of patients because their treatment, the reason they receive treatment is purely observational. They are not randomized. There's all this potential unobserved confound going on. So this patient you no longer use in stage 1, but actually you can use people here in stage 1. So the enrichment design basic idea is by using this enrichment sample, we can get more information to infer what's going on in stage 2, and which is a valid one because randomization is protects all this bias. When you go to stage 1, then when you compare treatment, we're going to use people here. We are not going to use enrichment sample because their treatment in stage 1 is observational. It's not randomized. So you cannot use them. So this basically is the idea of that. So, so now think about extreme case. Extreme case I described earlier. So basically it's like say, okay, there's no people here. So basically there's one trial here and another trial here. So basic idea is I can still use people here to infer what's going on for stage 2. Right? I know how people are going to perform, which medication works well for what kind of group of patients in stage 2, because this is a randomized trial. So once I know what's going on in stage 2, I can predict what those people, what's going on in the stage 2, right? So I can use whatever this kind of estimation and I can predict what's going on for stage 2, and use the prediction, pretend that this is like a smart trial. I don't want to use imputation, this words, but it's more like a prediction because those people never go into stage 2. But because I can use information from this enrichment sample, I can predict how they're going to perform in stage 2. And to make these two things together, I can pretend that I'm doing like a smart study. So that's the whole idea behind that. Okay, so and I just mentioned again is because sequential randomization is still play a bigger role here. Randomization protect a lot of things. This is like an extreme case I just mentioned earlier. You can think about there are two independent trials. One trial is conducted in stage 1. The other trial conducted in stage 2. And we saw like synthesize those two trials, make it like a smart trial. So, okay. So let me just now start, once I explain all this kind of idea or rationale, yes.
Just go back to logistics. So when you, in the first stage, you recruit patients simultaneously, but some of them randomized, some of them fully.
You don't have to recruit, let's say, simultaneously. You can say, okay, once you go to the second stage, now you can go back to the pool, try to see, okay, who want to be randomized in stage 2. You can still go outside and try to recruit people. Basically, like you're doing another randomization trial independently from this spot. So, yeah. You have a question? Yes?
Yeah, I mean, it seems like you have to be careful here with confounding. If you imagine this is like in inflammatory bowel disease, you can think of having more aggressive treatments first or less aggressive treatments first. You know, if you have a more aggressive treatment first, maybe nobody ends up, very few people end up in this group. So then you say, okay, let's look observationally at people who had more aggressive treatments first. Well, that's going to be a poor prognosis.
Yeah, I know. It could be, yeah. So let's go point. Like one key thing is obviously those two populations should be similar, because otherwise they should respond to drug the same way, because otherwise they're very different patients. But where I think maybe like, for example, in a study cost, you originally enroll those patients, but only 100 people can go into the study, and 900 can be candidate. So some sense like that, yeah. Yeah, there are definitely a lot of assumptions I didn't mention here, but that makes sense, yeah. All right, now a little bit more technical thing going on here. So it's like a notation-wise. So I use stage 1, stage 2. So you can see I use the subscript 1 means stage 1. 2 is like stage 2. And the S is like we call the state variable. You can think about it as covariance. It's all the covariance you want to use to try to do person medicine, how you give treatment. So A is like treatment notation. So here I think we just look at the binary treatment. That's the easy way. And the stage 2, you also have state. S2. So S2, actually, what I write here is very simple notation. Include the baseline, basic first stage covariance, first stage treatment history, but also can include this intermediate outcome as well. So they all can go to S2. A2 is a treatment. So, and the final outcome, I use Y to denote it. So as I mentioned earlier, DTR is a policy, is a decision function. So it's not like say treatment 1 here, 2 0 here. No, it's not. It's like a function. Basically, is a function maps covariance at the stage 1 to treatment in stage 1. And also the stage 2 is a function map all the information up to stage 2 to the treatment assignment in stage 2. So basically DTI is 2 functions, D1 and D2. Okay? So now the question is, suppose I give a policy, I give you 2 functions, T1, T2, how we can tell this policy is good or not compared to like standard treatment strategy. Well, the data here I just mentioned here is this is typical smart sample. So you have S1, A1, but because there's some missingness, there's some dropout, I use ZI to denote missing. And also enrichment sample, remember we only have S1, A1, A2, YJ, but point we know is for enrichment sample, A1 is not randomized. So A1 can depend on something not observed in the data. So, okay, so once you have that, so this is assumption. Kind of answer one of your questions. So first is we try to avoid this missing data issue. So we say a dropout is totally non-informative. So because otherwise this going to kill a whole even single trial. So we just make this a standard assumption. The second assumption is can relate to what is that these 2 populations between enrichment population and the original smart population, the outcome, the treatment response should be similar. I mean, how they respond to the drug, they should be similar. One cannot be like high risk and there is low risk. They'll be totally different. And so this is the kind of assumption we need. So once you have that, so this is the key thing is how we really want to use this 2 sample data to infer any like a potential outcome you are interested in. And this is a notation, hopefully you can follow me. So this Y is like a potential outcome, Y, you can think about that. So this means like if this patient is given treatment A1 and stage 1, treatment A2 is stage 2, and given whatever covariance you have at stage 1, and based on this sample, you can estimate this one in the stage 2 data, you can estimate using this kind of formula. Well, probably you don't, it's very complicated, but my point here is because in the stage 2 it's randomized. So potential outcome can really be inferred by use observed outcome in terms of average because it's randomized. So this is basically, this is observed data from original smart sample, and this is enrichment sample. Okay, so basically you just take original smart sample observation plus enrichment sample observation and take average. Then you can infer the potential outcome at the second stage given treatment A1 and A2. All right, so once you can get this sample from both data, so when you go back to first stage, how are we going to deal with this potential outcome? So basic thing is, when you go to first stage, so because some people continue in this second stage, some people don't. If they continue to second stage, of course their Y is potential outcome. It's the same as treatment A1, A2. But if they don't, so how are we going to get the observation or the outcome? What we do is we just use this prediction. That make sense? So what I'm trying to say here is, for the people who don't continue to the second stage, we don't observe them, right? We don't observe their potential outcome. But actually, because in the second stage we have both people who remain in the second stage, plus people you recruit, like an enrichment sample, we can use their outcome, try to infer, try to predict what's going on for those patients. Okay? And the reason we can do that because second stage is randomized. It's randomized. So let's key. So let's kind of think, but of course there's a weighting going on. Weighting just try to adjust what's probability assigned to treatment A1 versus A1, A2. Okay? So this is the formula. So basically it's like, say, when you go to the first stage, we follow who people continue to the second stage, you use this weight. People who didn't continue to the second stage, you use the prediction you obtained from previous slides, but weighted by this probability. All right, so there's a complication here. Once you get this Y outcome, then you can calculate what's the expectation of this potential outcome for given treatment policy D1, D2. That's how you can do that. And then you can come out with this variance formula, so I'm not going to do that. And then once you have, once you can get a potential outcome, average outcome for the policy D1, D2. Remember, D1 is treatment policy stage 1, D2 is policy stage 2. And then you can compare any two different treatment DTRs. So this is one DTR, D1, D2. This is the other one, D1 tutor, D2 tutor. So you can just take a difference and try to compare. And then you can assess which DTR is better compared to the other one. Okay, so because it's design issue, so obviously we want to demonstrate why this smarter can be better, and what kind of situation this can improve for your design efficiency. So that's what we, in this few slides, we do efficiency analysis. But because it's so complicated, so we should make it a little bit simple. So first we make a randomization to pure randomization. So in other words, randomization probability is constant, doesn't depend on individual. So like probability is P1, one arm, the other is P2. And we are assuming complete random dropout, so and we assume dropout rate is alpha, okay? And the stage 1 distribution between two samples are similar. So once under these simplified conditions, we can calculate relative efficiency smarter compared to original smart. What does it mean? So suppose you want to detect some certain difference. Original smart say you need a sample size n. And this relative efficiency basically tells you, okay, so if rho is bigger than 1, which means if I use enrichment sample, and this smartest should has more efficiency compared to original smart. So that's kind of how we get this relative efficiency. And then you can see this number depends on quite a few things. So first, of course, depends on alpha, which is the dropout rate from first stage. How many people drop out from first stage in original smart. And the beta is the relative proportion of enrichment sample. So if beta is 1, which means enrichment sample size is the same as original smart sample size. So beta equals 2, which means you double enrichment. So, and also there's other quantity, of course, depend on P1, P2, which is randomization probability, but also there's gamma. Gamma tells you sort of like a heterogeneity of across subgroups. So the gamma is more like a response profile across the patients, okay? So this summarizes efficiency again. So one interesting thing here is like if you look at alpha equals 0 case. Under this simple scheme, if alpha equals 0, which means everybody drop out from first stage 1. So what we are really doing is we conduct two independent trials and combine them, right, in this case. In this case, we can show when under some simplification, even beta bigger or equal to 1, actually we don't lose the efficiency compared to original smart. So in that case, in other words, if we conduct independent trial, and the second trial has same sample size as the first trial, so it is essentially is like we're doing smart design, a smart trial. So, but this is under some simplification for the gamma, for all these kind of parameters. So let's kind of efficiency we have. Maybe I can show you this table as well. So this table, we looked at different dropout rate from first stage for smart design, and this is enrichment proportion beta. So which means like 0.5, 0.5, which means in the original smart design, you have a 50% go to second stage, 50% of people they don't go to. But you in the second stage, you enrich 50% the original sample size people into second stage. So you can see theoretical relative efficiency is 0.87, and this empirical, which means we did the simulations and we looked at the actual variance ratio. And you can see those two numbers kind of close, which means our theoretical formula kind of is a good approximation. And the good thing you can see in this case, if only half of people go into second stage from original smart, but the enrichment sample is same sample size as original smart, we almost have same smart efficiency. So we don't lose efficiency. So it's like 1.15. But if you enrichment more people, then you gain efficiency. It's 1.26. And the same thing for the other scenario as well. And this shows a contour plot for efficiency gain for different alpha and beta. And the red line is which means the efficiency is the same as original smart. Okay. All right. So now we move to like summation of this part. So we conduct summations to see how really this kind of design can improve estimation or efficiency, variance estimation, or type of thing. And this is one study we conduct here. So this original sample is n equals 800. And in the first stage is pure randomization. In the first stage, second stage, they're both pure randomization. And for simplicity, only one baseline covariance, S1, has 3 values that go into this, this DTR. And this shows, this is the final outcome model. So in other words, if you give treatment A1, A2, and your covariance value at the baseline S1 is given like this, and your final outcome is given by this expression. Okay? Now we want to look at this particular DTR. I forgot how we came at this one, but let's the kind of particular DTR we have. So basically, this DTR is what? So at the first stage, if baseline variable S1 is smaller than 2, then the treatment should be assigned to 1. Otherwise, assigned to -1, which is the other treatment arm. Then in the second stage, you do the similar things, but you compare to 1 instead of compared to 2. So this is one typical DTR. And we want to compare this DTR value compared to one size fits all. One size fits all, which means the treatment at each stage is constant, no matter what kind of covariance S1 it is. Everybody going to give the same treatment, like 1 in this case. Okay. All right, so we also have another summation setting. So this second summation, we, in addition to baseline covariance treatment A1, A2, we also introduce this intermediate outcome. So you can see this is S2 is some observed outcome between stage 1 and stage 2. So in other words, you have a covariance S1, but you give treatment A1, then you have another intermediate outcome, S2. And then once you have S2, then outcome going to depend on everything, including S2. Okay? And then now DTR can also depend on intermediate outcome. So you can see first stage treatment policy is given by like same as before. So, but when you go to second stage, the treatment decision not only depends on S1, A1, but also depends on S2, which is intermediate outcome after stage 1. So this is another DTR. And again, we want to compare this DTR, compare this treatment policy to one size fits all treatment, okay, to see how it works. All right, so we run summations. We look at the different alpha, beta, and the reminder alpha is what is the proportion people who drop out from stage 1 in original SMART study. And the beta is enrichment proportion. So in this case, like you can see, everybody drop out, nobody continued to second stage, alpha equals 0. And this is like a 50%, 100%, 200%, we add the enrichment sample in the second stage. And you can, the first half is tells you how we estimate value of this particular DTR. In other words, what's the expected outcome for this DTR. So I forgot true value is 1.667. So you can see using our approach, estimate is bias is very small, and the coverage inference is reasonable. And this shows the efficiency gain. We compare the original. Suppose nobody drop out, you run SMART trial. How much efficiency gain compared to original SMART trial. So in this case, we don't gain efficiency. It's only like 0.647. But once the enrichment sample is the same number of patients recruited in the stage 2, then you can see like we get 23% efficiency. So and this is a comparison between two different DTR. Basically, it's the DTR I mentioned earlier compared to one size fits all. So we compare difference between those two. And then you can also see our inference is reasonable, and also we can gain efficiency when you have a larger number of enrichment sample. Okay, and this is for second summation, and the conclusion is about similar, so I don't have to repeat here. Okay, one important thing I want to mention here, even though this paper we only briefly mention here, but it can be a lot of things open in the future, is so far everything I've done, even include sample size calculation, everything is for fixed DTR. So in other words, you give me DTR, if I want to design a study, instead of do smart trial, do this smarter, smarter study, what's the sample size, right? But remember, when people go into DTR, the most interesting here is they want to discover they call optimal DTR. The optimal DTR, in other words, suppose you run smart, you have data collected. How are you going to find the best personalized DTR for every individual? So in other words, patient come in, you observe their covariance at the baseline. You need to decide what treatment to give to this patient. Then you follow this patient, you get the other observed like intermediate outcome. How are you going to decide what's the best treatment for this patient? So on. So this is about optimal DTR. And there are a lot of like analytical approach. People try to analyze data from smart design. So they basically use Q-learning, A-learning, and we use this outcome-weighted learning, kind of machine learning type approach, try to infer what's optimal DTR. And what I want to say here is, using this smart design, suppose you have data collected from smart design, you can also learn optimal DTR as well. And actually, you can still do a better job compared to just run smarter trial to get optimal DTR. So this is the summation setting with generate data. So we have covariance, treatment, or so on. And what I want to show here is this histogram plot. So this is the x-axis is the dropout rate from stage 1 when you run standard smart trial. Okay, so 0, which means you complete the whole trial, nobody drop out during the middle. So you can see when you run standard smart, and you complete the trial, and you can see the expected value. So how to evaluate the optimal DTR? Basically, you evaluate the average benefit under this policy. So this higher means better. So you can see on average is about like 3. Now, when you have some proportion of patients drop out from stage 1, for this case, 25% people drop out, and you use the remaining people in the smart, and you can figure out the optimal DTR. And you can see value is not like as good as like the first one, because obviously you don't have more data. So it's a little bit lower. Oh no, actually yellow one. So I should look at yellow one. So it's lower. And then when you can have more and more people drop out, and then you can see the value is not as big as this one. But what I want to show you here is this like a blue one, light blue one, is if we do enrichment sample. In other words, even if we have 25 or 50% dropout from original smart, but we enrichment sample, which means in the second stage, we recruit the same number of patients and add into original smart, make a smarter trial. And then we can use those samples to learn optimal DTR. Then you can see once we're using this enrichment sample, this value function about similar, only at the last step, they're a little bit lower. But you can see it's obvious it's much better compared to don't use the one without the enrichment sample. So that tells you you can use this kind of enrichment idea to bring more patients into each stage randomization. And by using more patients, you still can recover original smart in some sense. And you can still have a good power, to infer what's optimal dynamic treatment regimen for each patient. So that's basically what the message I want to give to you. Okay, so and again, so remember I previously showed you one example. Show you this two-stage smart trial, and we use this example as illustration, try to demonstrate how much gain we can do by using enrichment sample. So I just quickly show you, say, like for example, say, look at this line. So this say, suppose this two-stage trial, you have 40% of people didn't continue to stage 2. So if you run standard smart trial, you need 337 patients from beginning. Okay, the accounting for this dropout rate. But if you run smarter, suppose you use smarter, and in the beginning, in the first day, you only recruit like 202. But the enrichment sample, you only need 54. So your total is like only 256 compared to original 336.7. And that means like by using smarter design with this fewer number of patients, we can gain the same power when you try to look at the comparison between two particular DTRs. And the same thing for happen other things. But not just only no number, but one thing you can think about, use enrichment sample, you are trying to manage a smaller trial compared to originally manage a big SMART trial, two-stage randomized trial with 337 patients. So you can say management operation-wise is much easier compared to measure like a whole SMART trial. So that's another thing I want to conclude from this example here. So, okay, so how much time do I have? 50? Oh, great. I'm talking very fast. So, great. So, so conclusion remark is what I'm saying about your enrichment can help SMART to improve efficiency, try to salvage a potential high dropout rate or high non-compliance in the original SMART trial. By enrichment, you can also ensure sufficient sample size at each stage. Because this is sort of like it's not like a handle sequential randomization for a single cohort. You are doing basically at each stage, you go out to the study population and try to recruit new patients. So that's the basic idea too. And also, more efficient can begin if we can account the intermediate outcome. Actually, I didn't elaborate in the summation study, but you can observe from summation study. And the extreme case I mentioned earlier is you can just synthesize two independent trials. I know it's very aggressive in this sense. So in some, but under certain assumptions, you can just basically conduct an independent randomized trial at each stage and just combine them and make like a SMART. And you can still infer what's the optimal DTR for the patients. So, okay, so this is the caution when I don't want to say too much about that, but basically is I mentioned earlier, enrichment population and the SMART population you need to worry about. So what kind of enrichment sample you want to include? You want to make sure they are from same population. Otherwise, would be not practical and it would be biased. And also, like the quality of first stage treatment delivery should be good. And also, remember, like also for enrichment sample, one key thing we also need is we need to know what's their history. What's going on with this patient in stage 1. So you should be able to have some way to retrieve those kind of information. And also, enrichment sample may not be useful for first stage treatment if it's a novel treatment. In other words, because those people recruited in the second stage, the treatment they receive in the first stage is already drug on the market. It's not a new treatment that you're going to look at. So this kind of thing will be discussed. Thank you. Let's stop here. Yes.
So for your enrichment, I mean, the first of you assume that the dropout is not informed.
Right.
But your enrichment is trying to compensate those dropouts. So if dropouts informed, if you can characterize your dropout, do you think that you can potentially enrich your samples of the dropouts?
Well, I think so. Yeah. Well, this depends on how informative dropout is. Well, if a dropout is really very informative, depending on this potential outcome, even without enrichment, the original trial is biased, so we know that. But if we can characterize dropout patients, I mean, you know what's going on, you can predict well of them, so enrichment sample can give you more efficient gain about the prediction. Because, or you can see a whole idea about enrichment is you can use enrichment sample in addition to original sample, try to predict well for those people who didn't continue to the second stage. So if you can know what's going on for those dropout, you can make sure your prediction is good too. So you can do that too. That makes sense? Yeah. Yes?
So I'll ask a question I asked Libas yesterday, which is, in your simulation scenario 1, I think you included the possibility that one size fits all would be a good philosophy. But it seems to me the things that people don't check by randomization is the idea of reacting to outcomes at all. So you could have a design which was even more randomized, in which you had an arm at the very beginning, a control arm, who would just be randomized to not be screened in any way, not to have anything to it, just using best treatment. That would be the equivalent of your simulation scenario. As far as I can tell, nobody ever does this.
Well, in simulation we compare just constant treatment, but you're right. In practice, people just use best treatment, whatever they find from each one. But this is still like I think it's called, like I mentioned here, is in Collins. Maybe I can point the conference. That's what it suggests. But one potential thing, let's see, right here, I did mention this reference. So one thing, like exactly what I mentioned here, when they do sequential stage, they do different trial and they find the best treatment, and they use this best treatment as treatment at stage 1, and they use second best treatment as treatment 2. They do that too. But the one thing we compare our approach to this one, we know this one is not correct one because they don't account for long-term effects or delay effects of treatment. They only use the current, the best one they think. Osmation didn't do that. Osmation didn't do that. We just randomly pick one treatment for comparison. So.
Yeah, so I mean, it seems to me there's an element of all of this which is not randomized. This is the very idea of using a dynamic.
Yeah, I know.
That very idea itself is taken for granted. And at one point in your lecture, you said, since patients respond differently to treatment. Since. But what evidence do you have that that's true? And what evidence do you have?
Oh, well, they have a certain metric. I don't know if it's a good one or not, but their metric in the between stage 1 and stage 2, for example, they can measure how long they respond. Like for smoking cessation, they can see how long they quit smoking.
That's not a causal observation. That's just an observation. It's not a causal effect. The word response here, again, is the way to use the word response. The word response is observed to have a good outcome. It's not the same as is caused to have a good outcome.
But we make a decision, it only depends on observant, right? We're not what I'm saying, like, we make a decision in stage 2, you have to base on observer. You're not based on cause of thing. There's no way you know what's the cause of thing, right?
No, that's right. But the question is whether it's worth responding to. Whether it's worth you responding to what you see. I mean, so I would like to have it concrete. Give me an example of a disease. Give me an example of a disease and a definition of response. So a particular disease you would apply it to, what is the response you would use?
Right.
You mean an intermediate response?
Yeah.
Yeah,
What is the response you use at the phase 1?
For example, the
Like-
MDD,
In what was that?
major depression
Yes.
disorder, you can choose the response as response rate.
So response would be a reduction in the Hamilton score.
Right.
And what is the variability of that reduction? The within patient variability is enormous.
Yes.
So what happens immediately is you will misclassify lots of people as having responded to treatment who didn't and vice versa. This will immediately happen at this first phase. Response is a purely arbitrary thing. It's a reduction of 10 millimeters to 10 points on the Hamilton compared to baseline or something like that. It's,
Right, that's definition of response is based on some average across patients. For each individual patient, it might not be the best optimal treatment.
and it's known the regression to the mean effect is enormous. So what will happen is that all of those who are non-responders on the first stage, many of them will respond the second time. Of course, your randomization is partly taking account of that. But the problem is that the initial supposition that there is this enormous difference between patients, which is what everything that this is posited on, is not very well supported by further information. That's what frustrates me about this.
But it's still better than not adapting.
Not necessarily. Prove it to me. That's why I'm asking about the first stage randomization. I am a cynic who believes nothing. Prove it to me. Prove it to me by the standards that are used to register drugs in general. It seems to me that the whole smart philosophy is getting an easy ride compared to what would be required for any standalone therapeutic outcome, where for the whole strategy, it would have to be a randomization. Here, the very first bit, there is no randomization. The very first bit of deciding to have a smart is not randomized.
Actually, the randomization is not compared to placebo, but it's comparing to a lot of, in terms of effectiveness research, compared to a lot of
Okay,
things.
so let me give you an example of what I mean. So, for example, in ulcer, a great breakthrough was the development of H2 antagonists and so forth, and we had Tagamet, the #1 drug in the world, and then eventually along came meprazole was better. So I haven't followed the field anymore, but let's imagine that low-sec meprazole is a default treatment. Now, you would have some people who take low-sec and don't respond, and so you can imagine what we should do is do a smart design and see whether we should switch them to ranitidine or whatever, and we can do that. But in doing that, immediately it seems to me natural that what you should do is you should compare that whole strategy, that whole idea of the alternative of just treating people with meprazole or whatever.
Oh, yeah, we can compare.
Yeah, we can compare anything here. So.
So you have a first stage which is just compared to those.
We can compare that.
Yeah, we can compare.
See some examples of that.
Yeah, we just didn't have it in the simulation, but we can compare any DTI in this case. We just probably don't have power to do that. So. Oh, self-harmless? I can take a question? All right.
So when you compare this enrichment with the original smart design, I'm surprised to see that you even have smaller sample size, you can achieve the same efficiency. How come? The intuitive reason?
I think the intuitive reason is when we try to make this prediction, we have this stratified variable S1. I probably didn't show it, like related to gamma. So yeah, whereas when we do prediction for stage for those people, we're not just naively just use the mean of y try to predict those people. We looked at their specific covariance as well. Maybe I can go to here. So we look. Oops. We looked at stratify based on each S1. So yeah, we can make a prediction very accurate and make a variability reduced. So if you do already standard original smart, they don't use this prediction. Just take a rough average. Yeah, rough average. So let's kind of.
Do you assume your enrichment sample also have some dropout?
That can be potential. Yeah. No, but we don't. Yeah, we didn't do that. Yeah. 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 Once going to dropout business, I think it's not. It's like it's universal for all the trials. So. Whatever how people handle in the trial, we're going to handle the same thing here. So, yeah. Yes.
Just a statistical question: is the estimator you're using non-parametric efficient?
That's a good question. It's non-parametric, but I don't want to say it's efficient. Actually, the way we are doing here, I don't think it's the efficient way. Yeah. It's kind of related to G computation, but you should have like augmentation term over there. We didn't incorporate here. So yeah, here we just want to illustrate idea, try to show this is a very simple way to do calculation. So, but that's a good point. Yeah, we know this is not efficient one. Yeah. Yeah. Right. Okay. Thank you.